So now we come to integrating. We're not actually going to integrate the log function. We don't really look at that until extension 2 integration. But what we can do is go backwards of what we looked at yesterday. So integrating derivative on function. That of course was our answer to yesterday. So if we're going back the other way, logically, if we can see it and it's set up such that the derivative is on the top of the fraction, the function's on the bottom of the fraction, then we know we must have the log of that function. But technically, it's the log of the absolute value of that function. So 1 over 7 minus 3x, it's close. What you're looking at with these polynomial type things is if the order of the numerator is 1 less than the order of the denominator, because of course when you differentiate a polynomial, you take 1 off the power. And so for this, it's a constant on top, so it's of order 0. At the bottom, you've got a linear function. So that's order 1. So this is a log situation. So I would like the derivative on top. The derivative is negative 3. So let's put it there. Balance it out. We get negative 1/3 out the front. So I now have derivative on function. So I know it's minus 1/3 the log of the absolute value of 7 minus 3x. Similar here. Again, same situation. We've got a linear function on the bottom. So I would like 8 on top. Actually, the main reason I did a second one like that is just to point out with fractions, sometimes you see the dx on the top of the fraction, sometimes you see it next. It doesn't matter. I mean, it all means with respect to x. So we have 8 dx on 8x plus 5. Balance it out. We've got the 8th out the front. 8th log absolute value of 8x plus 5. So here we go. Bottom of the fraction is of order 6. Top of the fraction, order 5. So it's a log situation. We would like 6x to the power of 5 on the top, so balance that out. 1/6 the log of x to the power of 6 plus 2. But you'll notice I didn't bother with the absolute value signs there, because x to the power of 6 is always going to be positive. And if you add 2 to it, it's always going to be positive. So I don't really need the absolute. It's not wrong to put them there, but I don't actually need them with that one. Here's an interesting one. 1 over 5x. So I would like the derivative on top. Balance it out, and I get a 5th log 5x. But alternatively, I could do it this way, but something strange happens. If I pull out 1/5 first, and then I've got 1 on x, which is derivative on function, I get a 5th of log x plus a constant. Now, normally we say we can't have 2 different answers, but here we can because they're not actually different. Look at the first answer, the log of 5x. I could use my log laws and rewrite that as log 5 plus log x. Log 5 is, of course, a constant. So it is still a 5th log x plus a constant. So these answers are actually the same, it's just the constants would be different, whatever the constant is. That's what makes these questions really fun to mark, because I might be expecting a certain answer, and you might have something different. And then I've got to work out, hang on, is yours actually correct, but because of logs, something's happened here. And that will be the same when you're checking your answers in the back of the book as well. You might not have the answer that's in the back of the book, but it doesn't mean you're necessarily wrong. Let's have a look at this one. We do not have the situation derivative on function because they're both of order 1. What we do in this situation, whenever you see the order of the numerator is greater than or equal to the order of the denominator, do yourself a division first. So polynomial division, if you really have to do the full thing, that would be what it is. Or you might spot it. It doesn't really matter which way you come up with the answer. But we could rewrite that as 2 minus 1 over 2x plus 1 once we do our polynomial division. The 2 we certainly can integrate, but now our fraction, the order is 1 less in the numerator than denominator, so we can do it. It's a log situation. So we'll end up with 2x minus a half the log of 2x plus 1. Let's do a definite integral. Oh, lovely. We already have the derivative. Nothing for us to do here, because 2x is, of course, the derivative of x squared. So we know it's the log of x squared plus 1. Again, notice I didn't bother with the absolute values there, because I know x squared plus 1 is always going to be positive. Don't need it. Sub in 2, sub in 1, we get log 5 minus log 2. Pulling it together using our log laws, log of 5 on 2. It is okay to jump straight from the third last step to the last step. You don't really need that middle one, because if you remember, if you're summing into a log, you know you're always going to end up with log minus log. So you know it's going to be a fraction. So you just substitute in, and the top number goes on the top of the fraction, the bottom number goes on the bottom of the fraction. But take care. You cannot integrate across an asymptote. Brings me back to the hyperbola 1 on x. You could not do an integral from, say, -2 to 1, because you're going across the asymptote. Oh, differentiate x cubed log x and hence integrate x squared log x. Differentiate. Write down the first, diff the second, plus write down the second, diff the first. We end up with that. Oh, not quite. There's a bit more happening here, because now we can say the integral of x squared plus 3x squared log x is x cubed log x. Move the integral of x squared over, and of course divide by 3 as well. So it certainly had something to do with x cubed log x, but it's not just a straight multiple of it. Enjoy.